Saki mbwembwana kwele mchele kwa kuku kumwaga. Sako na wapenda yatusema nitasikia.
My name is Dr. Freeman. I'm a chemistry teacher and research director at Greens Farms Academy here in Connecticut. And my friend Lila Wells is asked me to do a video on heat. And so I thought I would do a little simple reaction and show you the equipment and some of the calculations, and then start off with a little bit of a background. How can we go about doing this and calculating these things? So the theory comes from conservation of energy principles, which I have behind me. I want you to imagine a chemistry system that has surroundings and then isolated surroundings, that is, from the rest of the universe, so that everything in terms of heat is taking place in this area here. And there's two possibilities. This system could actually give heat to the surroundings, or the surroundings could be inputting heat to the system, depending on what the system is, and in this case, a chemical system. So if we determine that the Q system has a value that is negative, it's going to be exothermic, which means it gives off heat to the surroundings. The surroundings temperature will increase, as opposed to a system that would be a positive heat, which is referred to as endothermic, meaning heat is entering the system from the surroundings. Surroundings is ample temperature for which to drive the reaction. Again, the conservation of energy is what all this is governed under, which is the first law of thermodynamics. And the system and the surroundings together, they don't create or destroy energy, as you've learned maybe in 6th grade, but that's why we have the 0 there. But we can relate the system heat to the surroundings heat, because the experiment I'm about to do is that we're measuring the surroundings and then we can relate it to the system. So let us get to the equipment that I'm going to show you. So I'll just play with my camera here a little bit. Sorry if I'm out of screen here. I have some water, and I have a calorimeter cup. Now this calorimeter cup is where everything is going to be happening. So it's basically right in here. It's got the system and the surroundings. And we have to keep all the heat in here, so I have it double walled. And I also have a top so that the heat does not escape the top. And we need to gauge the temperature, so I have a little trusty thermometer. And so the first thing we're gonna have to do is take the initial temperature of the water, because that's where the reaction is going to occur. And you want to use water that's been sitting around for a little while, so it's come to room temperature, and mine's been sitting for some time. And I've been measuring 24 for the last 5 minutes, so I'm going to take that as a good temperature. All right, so 24 is the initial temperature of the water. There's 100 milliliters in this graduated cylinder, so we'll keep track of that too. That's an important part of the calculation. And I pour all the water into the calorimeter cup. Here's the calorimeter cup. And then I have exactly pre-weighed 5 grams of calcium chloride. That's CaCl2. It's all here. And what I'm going to do, and before I do anything, is I get myself set up. So I have to have my thermometer ready to go, okay? And I have to have this. So I'm going to pour it in really quickly, close it up really quickly, then stir, and then watch the temperature. It may go up, it may go down based on the model behind me. And let's see what happens. So I'm going to fix my camera a little bit. Here we go. And there it is. Okay. That's good to stir it. And I can stir with the thermometer is one way to do this. And I'm already beginning to see that there's a temperature rise. It's starting to go up. So think about what type of reaction this might be, whether it's endothermic or exothermic, based on the temperature going up. Everything has to dissolve, so you got to keep stirring it. And what I'm going to do is take whatever the maximum temperature is, since it's going up. I'm going to take that as the temperature of all of this dissolving. I still hear dissolve. I still hear solid particles, so let's see if you can see that. And it's starting to go. It's gone up close to 2 degrees C at this point. It's still going up, so I'm going to keep stirring. I don't hear it clanking as much, so maybe the solid's getting close to being completely dissolved, because you don't want to stop until it's all dissolved. Calcium chloride, by the way, is one of the reagents that's used when you treat roadways that have been filled with snow and ice, and it helps melt the ice away. It's a different property known as colligator properties, but worth mentioning. Its heat properties are very important, which is one of the reasons I'm using it. I'm thinking this might be close to the end. I'm at 26, which is exactly 2 degrees C change. Just sneak a peek in here, see if there's anything left over. There's a couple little flakes maybe. I'm going to see if it gets up to 26.1. It's like 26 is as far as it's going to go. Okay, so I'm going to move my camera over here to show you some of the calculations. All right, so you can see behind me. There they are. So calcium chloride is solid. That's the white solid you saw. Was put into the water, and it broke up. It's a very soluble salt. Broke up into its ions, and that's why I use AQ for aqueous. They're dissolved ions in the water. You can't see them, but they're in there. And the delta heat of dissolution of that reaction that you just saw, I should be able to get somewhere around minus 82.8 kilojoules per mole. But there's always errors that are in experiments. And so this is no different than any other experiment. So I don't expect to get to it. I expect to be lower, but let's see what happens. So the equation that we use to get to this is how we relate Q in terms of the mass of the system, the C, and the delta T. Well, actually, we really can't measure directly the system. So what we do is we're measuring the surroundings, the water itself. So we're gonna get the mass of the water, and it was 100 milliliters. So I used 100 grams because 1 gram per milliliter is the density of water, so it's 100 grams. But I also had 5 grams of the stuff, the calcium chloride, so I added the 5 grams in there because it all dissolved into the water. And because it was a concentration that was very low with calcium chloride, we're going to assume that the properties of that water still water itself. So we're going to use the specific heat of water, 4.184. We had a final temperature of 26.0 and an initial temperature of 24. So that's a delta T of, yeah, it's still 26. A delta T of 2 degrees C. And now it's time to do a little calculation to see where we ended up with this reaction. 105 times 4.184 times 2 equals 879. We're going to say 880 joules of heat that was released to the surroundings. Now, the system, we're going to switch signs here, okay, because of the minus Q there. So we're going to say it's minus 88. This ensures that the delta H is going to be negative, which makes sense because all exothermic reactions that are negative are exothermic. So minus 880 joules over the number of moles of calcium chloride. Now, the number of moles of calcium chloride is the 5 grams divided by its molar mass to get to that. So that's another calculation that I'm going to have to do here. So that's going to be divided by 5 equals that times 110.98 equals that. And that comes out to be 19,500 joules per mole. Now we tend to want to use the correct units to compare. We're going to go to kilojoules per mole, which is 19.5 kilojoules per mole. 19.5 kilojoules per mole, that's a big negative, by the way. Negative 19.5 kilojoules per mole is very different from negative 82.5. So the issues tend to be that the calorimeter cup is not well insulated. It isn't. There could have been heat that was released one way or the other. It's possible that the calcium chloride was not pure, so there may have not been any contribution from some part of that 5 gram sample to advance the temperature. But the main error is right here. The delta T probably should have been somewhere around 7 or 8. We just didn't see that. So the thing about calorimetry is there could be differences from the expected value because of the calorimeter itself. But the actual technique itself is a fine technique to determine delta heats, and whether you're using basic coffee cup calorimeters or the most exotic calorimeter, the experience is that's the same. And I hope you enjoyed this tutorial, and hope to see you again. Thank you very much.
Nanipaga moyo nikianza kulia chozi nafutia.